Okay, good. So yeah, this session is about encoding data as NetCDF-CF, and then it builds on the previous session when we talked briefly about the fair data, etc. So I will go through the elements that I've set up here. So I will give a brief introduction to NetCDF as the file format, the climate and forecast conventions, and in particular the possibility that the discrete sampling geometries offer within the CF setup or the conventions. Then it's the attribute convention for dataset discovery, because that's quite useful. You are allowing your discovery metadata to follow your data through the value chain, and that's quite good. Then it's a brief introduction to X-array, and also I'm touching in on NetCDF-4, the Python modules, and a very brief introduction to R NetCDF for people working with the R software. The way I've done this is that I have a number of slides that I would like to go through, and then I've got a number of some Jupyter notebooks that people can look through. So I will use the Jupyter notebooks when I go through the introduction of X-array and RNetCDF. Both the Jupyter notebooks and some sample data I have uploaded to GitHub, so they are available in GitHub. So you will get a link to the GitHub area at the end of the presentation when I take my final slide. And the intention is that you can be grouped into small groups and just try this, collaborate on working on the reading the data, understanding the data, finally, so that you can play with the Python modules or the R modules for this purpose. When it comes to the notebooks, I've looked both at reading data, and for the Python example, I've also made a notebook for actually writing data in NetCDF-CF, and also so with the ACDD elements, and also with conversion of CSV files, because many people work with CSV files. So yeah, hopefully this is useful at some level. Feedback afterwards on what could be where you need more information and where you need less information would be useful. First of all, the reason why we do this is the fair guiding principles primarily. So when we do share data, we try to share data in a form that is readily understood by the consumers of the data. So you always try to document data in a manner that is understandable for people that do not have the detailed knowledge of the data. And the elements that we are focusing on today are not the findable and accessible, but it's more on the interoperable and reusable. So we are now discussing details about using a formal, accessible, shared, and broadly applicable language for knowledge representation. This is part of the CF conventions. We are using vocabularies, which is part of the CF conventions. Not so much on this, but that's actually possible to do as well. Yeah, and some of these elements as well. And it makes life easier when you try to share data to have them indexed in a searchable resource. So that's the elements that I would like to touch on. Just a brief revisit of the types of metadata for datasets. So we are now touching in today on discovery metadata. That's the ACDD, attribute convention for dataset discovery. And we are also touching in on use metadata, so the information that you need in order to understand the data that you find. And that's the climate and forecast convention, or the CF conventions. So first, briefly on the NetCDF file format. So what is NetCDF? It's the acronym is Network Common Data Form. And it's built on previous versions of what it was called the Common Data Form, which is actually still being used by many of the NASA communities, for example, for the for astrophysics and things like that. So this is an evolved version of those data format. So NetCDF is a set of software libraries, and self-describing machine-independent data formats that support creation, access, and sharing of array-oriented scientific data. So it can be anything, actually, and we will come back to that. You have a library that readily handles byte order of machines and things like that. You have a format that is suitable for large data sets and small data sets for that sake. And you have the ability to do built-in compression of the data sets or in parts of the data sets if you want to do that. And there are much more that you can do with NetCDF depending on the backend that you're using for NetCDF. So NetCDF was developed and is maintained at Unidata in the US. It's directly supported by the National Science Foundation and through grants from NASA and NOAA. So it will be around for a long time, and much of the archives of NASA and NOAA is built on this format. There is also an active group now, an expert team within the WMO, so World Meteorological Organization, looking into the further use and further defining profiles of the NetCDF-CF conventions as a WMO format. So it's mentioned several places in the governance documents of WMO. Unidata and a number of third parties are providing data and software tools that are useful for you, and we will go into some of them today, and I will give you links to some more. I think the most important thing, and where I started with using NetCDF, was with the programming interfaces, where I initially started with C. I've also used it in Fortran. And what we have in Python and R and in other things are built on top of these Java and C libraries. So that's the important element here. Programming interfaces are also available for Python, IDL, MATLAB, R, Ruby, and Perl. I don't know, perhaps even more. And if you want to know more details, I've just added the link to the frequently asked questions about NetCDF. So there's a lot of useful information on this, this page if you are not familiar with NetCDF. So more details on NetCDF. It's a self-describing format, meaning that the NetCDF file will include all information about the data it contains. It's portable, so you can send it around on the internet between different types of computers, and it can be readily understood by the consumer of the data. It's scalable, meaning that it can be used both for small data sets and large data sets. And there is even a process ongoing to make it suitable for object storage, like the new Amazon S3 bucket store and things like that. So using different backends for the NetCDF format, you can use it on different architectures. It's appendable in the sense that you can append information to a file. For example, if you have a data set that evolves over time, you can append data to the data set, and you can even aggregate across the files in a data set. So it has much useful functionality in this context. Yeah, it's shareable and it's archivable. I think I won't go into the details there, but it's quite important to remember that it will be around for at least 40 or 50 years, and it will be supported in that time frame, which is very good from the data preservation perspective in this context. So NetCDF files are containers like XML or other things, but it is a container that is structured in the sense that it's a container for dimensions, variables, and global attributes. So dimensions are spanning the data set, it's spanning the variables. The variables, that's the scientific content, so the either geophysical parameter that you're looking at or different things. And global attributes is further information about the data set, and ACDD elements, the attribute convention for data set discovery, comes into this category. Common misperception is that NetCDF is a binary format only. Important to remember here is that NetCDF can be converted to and from an ASCII representation using tools like NCDump and NCGen or Python or R. There is actually an ASCII representation of a NetCDF file that is known as CDL, and this is the common data language. I have an example of this how this looks like in on the right-hand side here. And this is the way I normally work with NetCDF file. When I try to understand the content of a NetCDF file, you use the NCDump functionality, or you open it in a tool like Panoply or something else, and you can look through the structure of the data set. And you see that in this representation of the data, it's quite easy to identify the name of the file, the dimensions of the file, the variables, the conventions here down there. These are the global attributes. And then you have the actual data that is in this data set. Comments are made using the double slash, and you can actually write a CDL file and convert it directly into a binary NetCDF file without actually doing anything else than just running it through the ncgen command. So it's quite straightforward to do that on a command line interface as well. There is another thing that I'm not touching into today, and that's NCML. This is an XML-based notation similar to CDL for NetCDF data. This is widely used when you offer data through an application server like Threads. You can do aggregations on top of files, etc. On this. For example, if you have yearly files of the temperature sensor in a certain location or a station, then you can aggregate all these yearly files into a long continuous time series using NCML, or the aggregation that is built into the application server. Concerning the structure, for this part, if you want to dig into more details, I would refer you to this link down here. So this illustration I've taken from the CEDA document in the UK. So it basically illustrates what I did in the last one as well. You have the common data language specification of the data, and it's actually showing the different parts. So you have the dimensions. So there is at least one dimension in every data set. There is a data type, so it's telling whether it's an integer or it's a float, and the number of bits that you're using for this. And then there is the actual data and how you work with them. So when you look at variables that looks like this, dimension, that is directly related to the dimension up here, then it's called, in the CF conventions, this is called a coordinate variable. So you are using it to span your data set. So I don't think I will go into more details about this. I do assume that people are somewhat familiar with some of these elements, but I think the important thing is that we remember that the NetCDF file is about dimensions spanning the data set. It's about the variables, it's the attributes, and it's the actual data. So there are different sections within a NetCDF file. Just to give you some overview of some tools that you can use in order to work with NetCDF. There is something called NCView. It's quite old, but it's quite robust as well. I'm not sure whether that actually exists and how well it works for Windows, but it works quite well on Linux computers, at least. NCDump, NCgen are command line tools that you can use in order to go back and forth between the CDL notation and the binary file format. There is, at least for the Windows users, this also works quite well on the Linux computer, software called Panoply, which is made by NASA, which you can use in order to investigate and check out and also plot NetCDF files. You can actually convert, if you have this tool, you can actually convert the data set to a comma-separated file as well and download it if you want to. Then you have NCO and NCKS, which are command line utilities, primarily developed for the Linux community, but it's also available on Windows computers. More interesting, perhaps for some, is that there is actually a plugin. I have never used this, but I've seen it referenced several times. There is a plugin for people working with Excel that enables you to actually read and handle NetCDF files within Excel that you can check out. And of course, then you can work with the data using Python, which we talk about primarily today, and R, and also MATLAB has very good tools for this. IDL was mentioned earlier. It's even understood by S3 software as well. So it's quite important to remember that NetCDF is actually an OGC standard. So it's one of the it's part of the foundation for the Open Geospatial Consortium and handling data. Sorry. So moving on to the Climate and Forecast Conventions, that's CF, and in particular CF discrete sampling geometries, which are quite useful for handling observations. So NetCDF and the CF conventions in particular comes primarily or originally from the modeling community, but it's been extended over time. So while it started off with a representation of numerical simulations, it's been extended into also represent the observations you need in order to validate or in order to initialize a numerical simulation. So the CF conventions. The CF conventions, there is a link at the bottom of the website, sorry, at the slide, if you want to look into it. This is the homepage of the CF conventions. And the CF conventions are metadata designed to promote the process and sharing of files created with the NetCDF API. This is true to the sense that it started off with NetCDF and it's primarily used within the community that is using NetCDF today, but the principles that are outlined in the CF conventions can be applied to a JSON file or to an XML file or anything else, but there is no standard approach in order to implement it in an XML file or JSON file today. But the principles as such are disconnected from the NetCDF as a file format. One thing I actually should perhaps mention in this context, for most practical purposes, NetCDF is more similar to a database than actually to a file format. If you compare it with, for example, a CSV file or an XML file or a JSON file, because within the you can have quite complex structures within a NetCDF file. The CF conventions are increasingly gaining acceptance and have been adopted by a number of projects and groups as a primary standard. So especially in the ocean community, but also in many other communities. It's also the backbone for data exchange in the WMO Global Cryosphere Watch. And WMO is now looking into the CF conventions because it takes your open container and make it somewhat more manageable. So you have comparable mechanisms for handling and describing the data sets. The purpose of the activity in WMO is just to further constrain the degrees of freedom when you put your data into a NetCDF-CF compliant file. So because although it's a convention, it's a quite wide convention, so you can put your data in there in many different ways, which actually slightly complicates the interpretation of the data, although it's still much better than actually having no standard enforced on top of the data. But the purpose of WMO is basically to say that, okay, if you have a weather station, you should do like this, and reduce further the degrees of freedom when you handle the data. The CF conventions generalize and extend the CORDS conventions, which was the original conventions, which originated primarily in the ocean community, also oceanography community. The ambition of CF is to locate data in space-time as function of other independent variables and to facilitate processing and graphical interpretation of the data. So that's why you have viewers like Panoply and NCView, etc., that directly shows the graphical interpretation of a data set. And finally, as I mentioned earlier, although it started as a NetCDF standard, most IDs relate to metadata design in general and are not specific for the NetCDF. So it can be used in other containers as well. The CF principles, which is basically the principles that determines both the development, initial development, but also the evolution of the standard, is that data should be self-describing, so no external tables or further information needed in order to interpret it. There is also a version of the NetCDF format now that allows linked data approaches, so you can actually link in information externally into the file. The conventions are developed only for the things that are needed, so it's not a design process where you think of future needs, but you develop or implement the needs as they exist. So that way, everything that is in there is actually used by part of the community. It should also be quite easy to use in the sense both for data providers and data consumers. There's always a definition issue there, but it's quite important as a principle. And the metadata should be readable both by humans and by programs or machines. So it's a machine readable format which can be automatically interpreted at different levels. And it's also quite important to minimize redundancy, and this you may encounter, for example, if you ask for new standard names, which we will come back to in the CF conventions. You may have some pushback from the governance structure, since they say that, okay, but you should instead use this already existing CF standard name, or you need to define your standard name according to the principles that they have defined, so that it's semantically consistent. So originally, semantic consistency was not part of the design principles, but it's been it's an element that has gained more and more attention in the community lately. There is also an attempt to avoid duplication or too many attributes, so it should be kept simple. So actually having good mechanisms for reuse and always checking if somebody suggests a new information piece within it, is it really needed? So that's a good principle. And information is generally provided per variable and not per file. So you can have information per file, but the important thing is that every variable should be self-contained within the file as well. And nothing depends on the names of the variables except one exception, and that's the coordinate variable convention, which we come back to slightly later. So I did say initially that ACDD is the discovery level and CF is the use level of metadata in this context. However, CF do provide some basic discovery metadata in global attributes. The challenge we do have here is that some of these are overlapping with the ACDD elements. And in general, I would say that we are following or try to follow the ACDD elements because those are more comprehensive and those are readily transferable into the ISO 19115 and GCMD diff and other discovery metadata standards. But basically, at the discovery level, the CF conventions include title, institution, source, history, references, and comment. So that's information that you can put into a CF compliant document. That being said, this in CF and ACDD, there are some elements that have restricted words. So there are requirements for some elements, some attributes, and the formatting of those. However, you can add as many attributes as you would like to your file. So a CF compliant reader will just ignore the exceeding information. So do not hesitate to add more information if you find it useful for the data consumer at a later point. When it comes to the use metadata, there are some elements that are mandatory for or useful and or mandatory for all variables in the file. So first of all, it's good practice to always add the attribute describing the units of the variable, even if it's a dimensionless number. Just put the unit 1 for those data sets. There should always, if possible, be a standard name that identifies the quantity. So this is about using controlled vocabularies in order to describe the content of the data. And the standard names comes with a reference to units in the standard name table of CF conventions. So you need to follow the units that are identified for the variable. It's always good practice to add long name. It's not required, but add long name. And if you don't have a proper standard name, or you have requested a standard name to be added to the CF standard names, and it may take some time, a couple of months perhaps, to have that standard name adopted. Anyway, do put a long name, your own words for that variable into the document, so that will always complement the standard name. You can have ancillary variables, and all numeric data should also have variables identifying how missing values are encoded. And the best way to do this today is fill value. You can also give the valid max and valid min of and valid range of a variable. It's not required, but it's good practice to add it, so it's easier for people to interpret the expected range of values for a variable. One note here is that although that you can use the attribute missing value, this is missing underscore value, it's not recommended practice to do it. So for now, it's only being kept as a for backwards compatibility, but it's actually depreciated in the CF conventions, so you should use fill value instead. And if you have variables that are containing flag values, you should add the flag values and flag meanings to make them self-describing in the output file. So this could be quality statements, quality indicators, and things like that. This is just a screenshot of a previous version of the CF conventions document. So this refers to the, I can get it, it's my mouse pointer. This is version 1.7. It's actually on version 1.8 now. And there are more or less continuous updates of this. And here you can go into various sections of the CF convention. You can look through and understand a bit more about how you set up file names, data types, naming conventions, dimensions, variables, how you encode missing data, value and valid and actual range of data, etc., and how you work with attributes in the data sets. So it's a very good and very comprehensive manual. If you have trouble understanding parts of the manual, please tell me, or please tell the CF governance structure directly, because there are also mailing lists that you can ask in order to have feedback on how to use the standard, and it's quite useful. Then you have other elements of the document. There is a description of the data, which we briefly touched in on. So we have to put in the units, the long name, standard name, always, ancillary data and flags, not always, but it's, I would say that it should be required always to use the first three, and the last two, it's up to you and decide depending on your data set. You can then give the coordinate types. So actually this is probably more useful for many of the numerical simulations. So if you are working with model data, but the time coordinate you should always add anyway. So that's quite useful. But longitude, latitude depends. If you have only one station, it's good practice to add the point also both in the global attributes as the ACDD elements, but also in the actual data as a variable. It seems, it can seem a bit redundant, but it actually helps in automatic interpretation of the data. There is a number of coordinate systems. I won't go into this, but here you also see that there are different mechanisms in order to handle different types of data. So you have, for some data, you do have also the model data. You have different types of grids that you can be working with, but you can also have, for example, time series of station data. You can have trajectories, and these things I will come a bit back to later as well. So if we go now through the next part here is the data representation within cells. So although this can be used and is often used for numerical simulations, it's also quite useful when you work with time series data or station or observations, for example. In my situation, if I'm working with observations from a weather station, it could be that this weather station is actually doing more or less continuous measurements of data, but what is actually stored by the logger is an average over the last 10 minutes or an average over the last hour or something like that. And using cell methods and cell measures is a mechanism to actually show this to the consumer of the data. I won't go into details about reduction of the dataset size, but you can do, if you have voluminous data, you can do internal compression in the file. You can also do, for example, you can represent a float number using integer values using a scale and offset parameter, which dramatically reduces the size of these data. And if you do that, it actually most interpreters are doing the interpretation of this data automatically. So they do understand scale and offset automatically. So this was the part I was discussing now. And then the last part is discrete sampling geometries. And for this, I think the most important thing to remember is features and feature types, because when, at least in SIOS, when we look for data, we always look for the global attribute of feature types, which I will come back to. Which can tell us that this is not a gridded data set. If we can't find the feature type in the data set, we will more or less automatically assume that this is a model or a gridded data set somehow. So it contains information about a spatial area in a grid somehow. And you can make, for the discrete sampling geometries, you can make the representation quite complicated. You can make very complicated NetCDF files for an observational data set. I would always recommend to make data sets as easy, as simple as possible, and rather group them together. And this also improves the usefulness for different data consumers out there. So leave the integration of data to the data center and the mechanism of the data center, and do not combine everything in one single large NetCDF file. That's more complicated to read, it's more complicated to use it afterwards, and it's even more complicated to share it broadly beyond your own community. A small note on the feature types. So here are some of the elements that you are able to handle within the NetCDF, the climate and forecast discrete sampling geometries. You have the ability to have point measurements. You have a time series at points. You have trajectories. You can have profiles, for example, a CTD station or a radiosonde station. You can have time series of profiles, or you can even have trajectories of profiles. So it depends on the nature of the data. Which one you choose should be linked to the potential data consumers of the data. So do not think only of your own use, but do think of other data consumers. For example, if you want the data to be used by the modeling community, they are normally not interested in cruises as such, but they are interested in, for example, CTD stations for the oceanographic data. So it can be considerations like that that you should take when you prepare your data set. So this is the final thing. There are actually in the CF conventions a very important section. That's the Appendix H. I think it's still the same numbering of this appendix, which contains annotated examples of discrete geometry. So here you can find samples of handling time series data, profiles data, trajectory data, time series of profiles, and trajectory of profiles. So these are always good to visit and consult when you do prepare your own data for publication using NetCDF and the CF conventions. This I've just added to show that there are actually now, as I said, more or less already support for points, trajectories, station data, profiles, gridded data, SWOT data, for example, satellite data, or other types of SWOTs. There are actually mechanisms for handling radial data, for example, a weather radar or different types of radar data in the NetCDF. And although it's in dotted here, there are mechanisms to handle geometries. This is the type of information that you normally would put in a KML or a shapefile or a GeoJSON file or something like that. The challenge of this, and the reason why I still keep it dotted, is that it's not widely adopted. So it came with the 1.8 version of the CF conventions, so I haven't seen much data in it yet. Although it's building on the principles that GMT was using for their map database originally within the NetCDF container. So some recommendations, requirements. CORDS requires CDL dimension in the order of time, altitude, Y and X. CF recommends it. So this is not a strict, this order is not a strict one for CF, but I think it's good practice to keep dimensions in this order. This also makes it easy to append data to the NetCDF files. Yeah, Unidata associates one coordinate variable with each dimension by identity of name. And this was the thing that I mentioned earlier. So if you have a variable with the same name as the dimension, this is a coordinate variable. So these are the values that are spanning your data set. So if I had time of time, that's the coordinate values. That's the temporal values for the, date time specifications of the data set in a time series, for example. Time is encoded with units, time units since reference time. So this is the way that CF works. So it could be seconds since the January 1st, 1970 or some other time, and you will see that in the Python examples later. The cell methods indicate how variation within the cell is represented. You will also see an example of that later. And if you want to look into more details of some of these comments, there is an online document indicated here. So you will get the slides after the session, where you can look into more details in this aspect. And then just to give you a small example of how this works in the in a file. So these are this is a NetCDF file containing some data from the surface irradiance station that Met operates at Bjørnøya. And you have a number of you have the dimensions up here. You have the variables down here. You also see that there are some information in here that is strings, and this has changed slightly since I created this example. But the reason why I put this in here is that we have the station name in a specific variable in the data set. The global attributes here are actually, so this is the old standard that we used at MET for this purpose, but you still have the ability, you understand the structure of the data. And you see in here, I put in the units, the standard name for the variable, also the valid min and valid max, in this case for a coordinate variable. If you look down at here the surface shortwave irradiation, you have here the standard name for it. You have the identification of missing values in it. You have the units, and you have this cell method. So this is a mean value over the last minute. So this is the information that the logger in this specific situation is putting on into the file. So this is an example of how you put up the file, and this is the CDL representation of a binary file. And if I put it into the NCView application, that looks like this, it's automatically plotted. So just for the initial discovery of the data, it's quite useful to use this. NCView is quite robust, but it's not very intelligent. You may also want to use Panoply instead of this if you just want to have a quick look of data. So I'm increasingly more often using Panoply than NCView now. And this is just another example of data. This is actually data from the Radioson station at Bjørnøya. You have the same setup for the data sets. We've here put in some other elements, CF role. It's not critical that you understand this, but it's detailed information on it in the CF conventions. But we are also using quite active now the axis attribute, so you can actually give relations on various variables in the data set. And this data set is also more or less then automatically interpreted by the divided into profiles in by the NCView. Important when you work with your own data is to find the correct standard name to use for observations. And if you go to the CF conventions website, then you will find standard names listed. This is an old screen dump, so this is more or less continuously updated. The functionality is the same. It's just the content that is added here that is amended continuously. And you can view elements or standard names by category, or you can search through all of them. So normally, if you want to say something about temperature, just type in temperature, and you have all standard names related to temperature. Then you can click on the specific standard name, and you will have a description of the standard name. And at the end here, you have the canonical units that you should use for this specific standard name if you present it in a NetCDF file. These two last columns you can ignore. That is for how people document these data if they're using the WMO grid format or the model intercomparison experiment profile for data. So there's a lot of things you can do in this context to work with the data in more detail. NetCDF is inherently related to the UD units package, or it should be UD units 2, which is a standardized way of describing units for variables. If you're using the standard names, use the standard name table for that. If you need to consult the UD units, it's possible to do it online. It's an XML-based setup that you can use. But I think normally none of you should have to do that in detail. Sorry. Moving on.
Sorry, Øystein, there is one comment and one question in the chat box.
Yeah.
From Julio. Is the variable dimension only the number of occurrences of the variable in the file?
So the dimension says if you have time, the time variable, so the time coordinate variable should have the same number of time steps as the variable in the file has, if that was the question.
Julio, do you want to comment that? Or
Yeah, hello. I don't get quite well the concept of dimension here. Maybe if you can recall in other words for me.
So, sorry, I had some trouble hearing you.
Yeah, do you hear me now?
Yeah, much better.
Okay, I was saying I don't get quite well the concept of a dimension in the NetCDF file. If you can you provide me an example?
So if you look here, you have the dimensions up, or perhaps this is a complicated data set. I will use this instead. It's much easier. So if you see here, you have the dimensions set at the top. So we know that we have two dimensions in this file. It's time and it's string length.
Okay.
So string length is just a technical way in order to have a variable containing the station identifier. So it's, I think we forget about that now. It's a technical way of doing it. But we know that the actual measurements we have in this situation, it's the surface downwelling shortwave flux, SSI, is a function of time and time only. So the dimension and the coordinate variable for this is time. So we see that time is unlimited, meaning that I can actually append new data to this file continuously. But it also says that currently I have like more than 3 million, almost 4 million data points in this, this file. And then the representation of each time step in this context is contained in the coordinate variable. That's the variable with the same name as the dimension. That's the coordinate variable.
Oh,
So,
okay, get it.
Okay.
Okay, thank you.
Good.
So maybe, Øystein, we should make like a 10 minutes break and then go to the ACDD, or you would like to have this before
I think if we can push through the ACDD and then we take a break and go into the Jupyter notebooks afterwards.
Okay.
Because this is it's quite hard to go into much details on the ACDD elements, except that the thing that you should check is these elements up here. Also this link, there you have a full description of the ACDD conventions. It's discovery metadata. So if you deliver a NetCDF file, for example, in the SIOS context, if we handle those data at the Met Institute, for example, we can extract the discovery metadata automatically from the file, and we can ingest it in the catalog, making them searchable. And also application servers like Threads and other things, other tools as well, can automatically extract information directly from the files and create discovery metadata from it. NILU is actually using part of this approach in their setup for the SIOS integration. There is also a link here on mappings between ACDD and, for example, ISO 19115, etc. So this information is more for the data centers, those representing a data center here. This is primarily for the data providers. What I will add to my presentation here is a link to a web page that we are maintaining at the Met Institute, with some core elements that you should put into the NetCDF file in order to have a more or less comprehensive discovery metadata set for your data set, data description. The remaining slides that I show here are actually copies from that web page that we are maintaining, but I forgot to put a link to this web page into it. So here is a number or a listing of the various global attributes that are part of the ACDD conventions, and that we are actually using. at top, it says ID and naming authority. These two are not critical, and actually it's often better that you leave them out unless that you're maintaining your own data set through an application server. So if you're a data center and serve your data, then you should use these. If you're delivering your data set to another data center that is actually taking care of it over time, then they should set the ID and the naming authority for this specific purpose. Then it's the title, it's summary, it's keywords, and keywords should also be linked to these keywords vocabulary. So in the SIOS context, we would like people to use the GCMD science keywords for the discovery metadata, but we are also working on automatically translating from CF standard names to GCMD science keywords. Then it's the spatial location of the dataset described here. You have the temporal specification of the dataset. It's the conventions, and here it should be because conventions is also part of the CF conventions. So here you need to put in a comma-separated list containing both ACDD 1.3 and CF 1.8 or whatever version of the CF conventions that you are using. So this can be a challenge for some checkers sometimes. Its history gives statements about the way that your dataset has evolved. Its source, its processing level. So these are not critical, but it's always good practice to have some information in there. It's the date created. It's the creator type. So everything that goes on creator here relates directly back to the PI of the dataset. If you have other people that have helped you creating the data, add them as contributor and use the same elements: contributor, institution, name, email, etc. If you have multiple names, use comma-separated list there. And then, institution is not necessary. This is actually, it's more important to use this creator institution and contributor institution. Publisher name and email and URL should actually be set by the data, also the data center, if you're not handling your own data set. If you know who will handle your data set, you can set it to that specific data center. And it's always good to add project identifier, whether it's Nansen Legacy or some other project. So first of all, when working with NetCDF in Python, I think I will just briefly mention two different approaches to it. One that's the more or less default or standard, and that one that I actually recommend because it has a higher level user interface or much more functionality built into it. First of all, you can work with NetCDF in Python using a module called NetCDF-4, a Python package. It's actually NetCDF-4 with lowercase n for NetCDF. This is a Python interface to the NetCDF-C library that I mentioned initially. In this, you have full control over the NetCDF interfaces as provided by the NetCDF API as Application Programmer's Interface. The downside is that you have to have full control over the NetCDF interfaces. So you don't get anything for free using this approach. And I do have a notebook providing an example on how to read NetCDF using this module. We'll go into that afterwards. I think one thing, so if you want more information about this module, I have put a link in the page at the upper right corner here. It's also quite important to remember that when you're working with dates that you need to take some care when you work with time zones. For example, normally I work at the Met Institute. All our computers normally run at the UTC time zone. Then life is easy. If you work in a different time zone, then conversions of dates and times can be affected by the time zone. So you may have a different output of your data than you actually expected. So that's why I just put up this reference to date time and the PyTSat module, so that you are aware of take some care when you work with time zones in when using this this module. This module and the approach I'm presenting here is quite similar to working with NetCDF in the R environment. I will also show you some examples of how to work with the R NetCDF implementation, and that's quite similar to this NetCDF-4 implementation in Python. They are both sort of modules that are built on top of the NetCDF API. So same challenges do arise with both of them. However, in Python, you also have a module or a package called xArray, and this is quite powerful. So this keeps metadata continuously throughout the value chain, and it supports multidimensional data. If you want more information about the xArray, I've put some links in here. You have this information about the package as such. You have a link to some fundamentals of xArray, which I think is quite useful. It's actually a good thing. And I've got 2 Jupyter notebooks providing an example of how to work with NetCDF and xArray, one for reading data and one for writing data. So that's, yeah. I think it's quite easy to work with this this xArray package. It has some loopholes that you need to be aware of. I think I've covered at least some of them in the Jupyter notebook. If you want to look into more examples, there are some links here. There are even more links available on the internet. So it's quite easy to find support material for this, this package. So this is, and you will get a link to this Jupyter notebook afterwards in the final slide. I put it on GitHub, also with some example data that you can work with that are not available on the internet. So this is for reading NetCDF-CF using the NetCDF-4 module, which I mentioned was built directly on top of the NetCDF API. In order to use it, you need to import it, and I normally do it this way in the sense that I import it with a short name so that I don't have to do all the long names when I use elements of it. You can also use from the module and then import some specific function, but that in large programs, then you often run into trouble at some point. In these notebooks, the data sets that are available on the net, I've added directly into the notebook so that you have it listed here. So these are weather station data from the Met station, also the Meteorological Institute. If you look through the data, so in this step, I actually do read the data. So now I have the data in the my file object. I would like to know which type of data this is, and this is a NetCDF-3 classic element. So you have different approaches to working with NetCDF data. If you have the NetCDF-4 part, you can actually use groups, etc., within the and grouping of variables, etc., in the and build hierarchies in the data set. But that is not compliant with the CF conventions as it is currently. There is an ongoing discussion in the CF community on whether to accept these groups in the CF conventions, but I haven't found a good manner of doing it without breaking the backwards compatibility. And I always try to maintain the backwards compatibility. So this is the fight in the community. So then you can check the structure of the data, and it's basically just write the name also of the object, and then you get all the information from the data set. It's not very nicely presented to the user, but you have all the information about the global attributes at the top here. You have the dimensions about. So now I'm reading over OpenDAP, so that's sad. So I do not have this file locally. This is I'm using an OpenDAP URL directly, and then I just connect to the data set over the internet, and I read what I need from the data set. I would like to know what are the global attributes in the file. Then I just use NC_attrs. So I get a listing of all the attributes of the file, which is in a list down below. If I need to access one specific attribute, I just get the name of that attribute. So I get it from here. I find title there. I put it in there, and then I get the output of that global attribute from this specific file. Then I would like to know what are the variables that are contained in this file. And I use the word variables and the keys. So I get the identifiers for the or the strings that are identifying these variables. And I get a dictionary of those keys. And if I want to check one specific variable, I use this specification, also the object dot variables and the name of the variable, and then I get a list of the information about the variable. And it says that it has a long name, it has a standard name, it has the units, etc. Here you can see that it's missing actually the fill value. So the missing values are not encoded in this data set, and it's quite important to keep in mind. I can check the units specifically if I would like to, using a statement like this. So I just add the specific attribute I would like to see to the top of the previous statement. And as I said, as you can see, fill value, it was not properly set in this document. And then I will get some trouble when I try to work with it, when I try to plot the data. So here I've been working with the data, try to plot the results. I'm using matplotlib pyplot as PLT, just to keep it separated from the other things. I'm using date time. I'm using this time zone to make sure that I do not mess up time zones when I work with the data. I create different. Also, I create a timestamp. Also, I go from timestamp to the actual date time object so that I can work with it when I'm plotting it. So here I have the plot statement of the date time. So I have proper rendering of time at the x-axis, and I have the variables. And you see that there are some spikes in the data set here that it doesn't work very well. This part I've forgotten to take away, so I will remove that afterwards. But then you can do quite easy a dump of your data to a comma-separated file. So if you're not familiar with working with NetCDF files and you want to continue in your beloved Excel spreadsheet or something like that, then you use Pandas, and you have the you create a data frame, a Pandas data frame from your data set. You can get a listing of this and just dump that data frame to a comma-separated file. So then you have your data set in a comma-separated file that you can continue to work with. The downside of that is that you lose all the metadata once you dump it to the comma-separated file, because there is no standardized way of maintaining that information in the comma-separated file format. So that was a very brief introduction to the NetCDF-4 part. And then I would also like to show another notebook, which is actually prepared as reading then NetCDF using the X-array module, which has a higher level of user friendliness, I would say, in this context. And now I use import array as XR. Read the data directly from the NetCDF file served over OpenDAP. So still, this is not a local file. It's something that I read on the internet. I have the link directly to the Threads server here. This information, the link to the file, you can actually find in the SIOS data catalog. If you look into data access and choose OpenDAP from the data access, then you will get this link and you can work with it. You can check the content, and you see that X-array presents the content of this data file in a nicer manner to the user. So you are actually here able to expand or collapse or expand contents of the different variables. So if I want to know more about the content of the variable relative humidity, I get now the long name, the standard name, and the units that has been used for this specific. And you can open and close these for all the elements that are down here. Then you would like to check the global attributes of the file. And then it's basically just adding .attrs, and you get a list of all the global attributes. If I would like to know the variables of the file, I just add .data_vars, and I get all a list of all the variables, including the data type that has been used for each variable. So here you see that it's float 64 or float 32 that has been used for most of them. If I want to access one specific variable, then I get the output here. I just put I use the name that I find up here. I put it in the quotes here, and I get back the data array that is actually representing this variable in the data set. So yeah, this is quite useful in this context. Now, if I want to plot the results, I have the problem that I mentioned earlier, that when I do plot it directly, I just add .plot.line to have a line plot of the variable. You see that there are some very large values in between here. These are actually missing values that haven't been properly identified in the data. What was to have a very quick filtering of the information, and then I plot it again, and I get a nicer plot of the data. And I haven't actually completed this filtering away the erroneous informations. Same as before, if you want to dump your data to a comma-separated file, you need to convert it to a Pandas data frame. And this is done just using the word, you can take the X-array data array object and just convert it by using the toDataFrame method. And then if I just list the top of these documents, this is the output. And if I put it in here to the comma-separated file, I will actually have the full content of this. I will have a comma-separated file with the output of this NetCDF file. So that's a very simple way to work with the NetCDF files, and also to convert it into, for example, comma-separated files if you want to work further on with them. But I think most of you would benefit from using the methods that are available within the X-array in order to further work with the data set. I did also add another notebook for this purpose, and that was how to create a NetCDF file from a comma-separated file using the X-array module. And as before, I'm using two elements here. I'm using X-array, because that has the nice functionality when you're working with CF compliant data. But I'm also using the Pandas package, which is nice when you work with the tabular form data, like reading and writing comma-separated files. And now you see that the file I'm working with is not a file that is available on the internet, but this is actually a local file on my computer. This file, however, is available to you if you want to play with it. It's on the in the GitHub area that I've prepared, so you can actually check it and work with it there as well. Then I use the Pandas read CSV function, and this you can control to great detail when you work with it. What you see here is that I do anticipate some information about header, and I do identify now the header, the record in the header that is identifying the variable names that I would like to use in this document. That's in the row 0. So indexes here starts at 0 and not at 1. So the first row is 0 and not 1. I also say that, and you will see this when you look into the file, because the date time that is actually used in this file is European style. So using day, month, year, and not year, month, day when you set it up. So I've said that it should actually interpret the date time format while reading the data, and that it should parse dates from the column that is marked with date time. And this one I get from this record that I identified in the record, also record number 0. And I also have to tell, that in this format, day comes before month. So this is because when you work with European style and US style date formats, then you have to make the system aware of this. Otherwise, you will have it wrongly interpreted, which you will quite fast discover when you try to plot the data. And once I've done this, I have the data in a Pandas data frame, which looks like this when I try to plot it, as when I show the content of it. And if I try to plot it, I get an illustration like this. So now I just said that I was supposed to plot 2 of the variables in this data frame. I was plotting the long wave, incoming long wave radiation and the incoming short wave irradiation. So in this specific data sets, there are actually 2 different set of instruments measuring the same variables. So that's why you have one with the same name, with one of them having .1 in the column name. So you can actually compare 2 different set of sensors using this this setup. It's actually a Kip & Sonen CNR4 and an Apogee SN500 that is has been put in this data set. It's only 2 days of data from a specific test site that we had. And you can look at the specific content of a variable. But when you want to put these data into a NetCDF file, Pandas is not good for that, but X-array is much better for that. So what I do is I create a Pandas dataset, an X-array dataset from the Pandas data frame. And instead of putting all the information from this Pandas data frame, I say that I only want the date time, the long wave incoming and the short wave incoming variables into this NetCDF file. And then I check the content of this data set, like I've done before, and I get this indication of the data set. And this doesn't look much CF compliant to me, at least. I have dimensions that are index and not time, so it somehow it didn't understand the specification of time here. There is no information, no attributes on the variables, so I don't have any clue on the units or anything on the variables that I do have here. And I haven't done anything on the missing values encoding and things like that. So first thing I do now is to rename the date time variable, dimension to time, because that was the requirement of the CF convention. I have a dimension that has a variable name with the same word as the dimension, and that's the coordinate variable. I could, of course, have called it date time, but again, and then I could have called the variable date time and use the standard name time for it. But I think it's good practice to always use time for the temporal dimension of the data set. So here I rename the dimension that was previously called index to time. And at the same time, I do also rename the variable that was called date time to time. So now I have a CF compliant coordinate variable in this data set. And if I write it again, I see that my dimension is now time, and I have an index that is time. And yeah, and then I specify time as the coordinate. So it wasn't done that wasn't done in the previous step. And then I do, sorry, set the coordinates, use the set coordinates method in order to specify it. Sorry for that. And in order to get rid of index as a numeric index as a dimension, I just reset the index of the data set. Otherwise, I would have two dimensions up here. I would have one for time and one for index. So now I only have one dimension at the top because I don't know the numeric dimension index anymore. Then I would like to add some global attributes according to the ACDD elements. So I did put some of them in here. I haven't done it completely, so that's something that you can work on if you in the exercise afterwards. I just add to this data set, I have global attributes, conventions, title, abstract, creator name, and email. And then I add those using this method. And if I just then show the content of the dataset, we see that in the dataset now, I also have the global attributes that I mentioned up here. Next step would be to add CF-specific elements on the variables. And I have two variables that I need to do this on. I need to do it on the long wave flux and on the short wave flux. I've put in units, I put in a standard name and a long name. I did not put in fill value here because if you try to do that, everything will fail. And this is not necessarily logic. At least it wasn't logic to me. I would assume that I could also put the attributes on the variables in this context, but I have to do the fill value in a secondary step further down that we will come back to. So that's why I've removed it from here. And we can now see that we've got more detailed information on the data variables down here. Then there is this loopholes that I mentioned earlier. Part of the trouble there is that when we write data using X-array have some default behavior that is not necessarily compliant with making data available through a threads data server or an application server on the internet. And one specific problem that we do have is that by default, X-array will output data, for example, time values in int64 values. So integer 64-bit values. This is not supported by the threads data server currently. I think it's in the process of being supported now, or it's come in some of the test servers. So that's why we need to constrain it to int32. And the way to do this is actually to set an encoding of the output. So while writing the data, you put some constraints on the information that X-array puts into the disk. So the NetCDF file on the disk. And one thing I've done here is that to say that the time variable or the time coordinate variable should be in data type int32 instead of int64. Then it will work on a threads data server as well. I've also said that I'm using now missing values encoded according to a specific standard. So this is done in this step and not up here as you would logically think that it should be or could be done. So you have to do it down in the encoding output. I've also added here something just to show that it's possible, but I can do compression internally in the NetCDF file. So I do not have to compress the full file. In a NetCDF file, I can choose to apply compression on specific variables and leave other parts of the file uncompressed. And this is the reason why I put setlib in here. If you put setlib equals to true there, you can add the compression level, and that will automatically be enforced on this specific variable. If you leave it like setlib equals false down here, this variable will be compressed, and this will not be compressed. And this is something that you have to check if you're working with datasets. Small datasets will probably be larger if you use compression. Large datasets will benefit from using compression, but you shouldn't use compression in the metadata elements. And there is quite a lot of elements in a NetCDF file that you shouldn't use the compression on. And in this last part, I've just shown there are two statements. One, you can check the NetCDF file afterwards on your own if you like to. What would the NetCDF file look like if you dump it to disk without using this encoding specification? And down here you have the result if you are using the encoding specifications. So this file you can actually serve through a Threads data server. The result you get here, you can't serve through a Threads data server. So that was the things that I would like to say on Python. Yeah, so this one, now we've covered through these two. And then it's just a very brief introduction to R NetCDF, also how to work with NetCDF in the R environment. And I personally are using the R NetCDF package, which is quite similar to the Python package NetCDF-4. It's basically the same steps that you have to do. You have to identify the library that you are using, so R NetCDF. You have to do every tedious step of the dataset. So open the file, and then you have to go through and get the content of the file with the get the attribute. It's the get the variable. You have to work specifically with the date time part to make it work nicely in there. And if you want to dump the data to a NetCDF file, you just switch all statements that have get over here with put. That's the quite straightforward way to do it. So in this context, like for the NetCDF-4 Python package, you don't get anything for free. You have to get through all the details on your own. Yes, that actually completes what I intended to present now.